Not listen to it. Good. Good. Okay, so let's start. So good morning or good afternoon, everyone. If there is any question, you can just ask it right away as usual. Put up your microphone and ask. So today I'm going to talk about monomization of morphisms. So the third and last technique that I wanted to present in the course. So today it's all about examples, statement, and then we're going to make considerations on the target to talk about some of the qualitative difficulties involved and what they mean, what kind of consequences they have for the problem. So I want to start with somehow a vague question here that we're going to precise in a moment, but I want to start with a vague. So given proper Q morphism, is there a resolution of it? So for now, we treated the case essentially of a function, and we look at it in a very specific case of the zero locus of the function, because as we said, our original interest was in the set, which was defined in the quasianalytic set that was defined by the zero set of that function. But we can, of course, ask this question for a general morphism. And in this case, we're not only fixing on the zero locus, but we also are considering morphisms which have several entries, not only just one entry. And maybe the root of this question can go back, which is a vague question for now, to the problem of factorization of birational morphisms. Which go back to Zariski, at least Zariski, in 58. So it's the first time that the question appears in a concrete way, or that actually a proof in a concrete way for the case of surfaces, the two-dimensional case. So it's a particular kind of morphism here, birational morphism, and there is a notion of what this resolution here, which is yet to be defined as. And since then, there are some sort of bifurcations of what this question should mean that kind of depend on the applications that one is interested in. So we can go back to the notion of monomization, which goes back to Hironaka, but also you can go even a little bit back. This notion already appears in low dimension, at least in papers of Abianca from 66. You have the notion of development of what is called semi-stable reduction, which goes back to work of Deline, of Mumford, around the 70s. And I can also want to cite the notion of the more modern notion of relative desingularization, which was recently introduced by Abramovich, Tame, and Godarczyk. Here in 2020. And these are all different notions of what this resolution might mean for us, which we haven't defined yet. But we're going to focus on the notion of monomization coming from Hironaka and Abianca, kind of because there is expected applications well, at the time for Hironaka to subanalytic geometry. For us to quasianalytic and else. So we do so in part, this is one of the interests here is that we know that we're going to choose the kind of this singularization or notion of resolution of the morphism, which interests to us the most, and this is basically what we want to apply. And so the question in a more precise way then can be formulated as let phi of Mn be a proper Q morphism. Is there a diagram, a commutative diagram, yeah, I'm gonna write this. Here's your phi, here's your tau, and here's some phi tilde, so this is commutative, where the sigma and the tau that we're making are finite sequences of blowing up, and this phi tilde should be as simple as possible. So the notion that we're going to give here is what we are going to call monomial. So what I'm going to do, I'm going to start in the next part. So this is the question that we're asking here. I'm going to start by defining what monomial means for us and what are some properties that it is. For now, we can just think of it as being like the simplest, and this is the kind of the heuristic I'm going to try to follow, the simplest kind of morphism that we can hope to obtain. And then we're going to state the main results and give some answers to this question, at least in this setting, in this category. Okay, so I'm going to start by precising what I mean by monomial. And I want to kind of build up from an intuition in order just to get to the final, to the working definition that we're going to use. So let's do a first approximation what it should mean, right? So we take phi of M in N, we fix such that locally at A, at a point A, we have coordinate systems such as we are used to, so coordinate systems in the source and target. And this time I'm not going to focus, not yet at least, in the exceptional divisor, so let's just make things simpler. Some coordinate systems. Say X, just like to take U in A, and let's say XZ at phi of A, I might call it B, such that, well, what we want is that the answers Xi are just going to be given by monomials, as we are used to. And maybe I'm introducing this other variable Z just to say that they are going to be terms which are equal to 0. I want to admit I don't want necessarily that all of the entries are non-zero. It's fine to admit some of the entries being equal to 0. So here one, say to some P, and now, and I'm going to use a strange notation here as prime, but it's going to make sense later on when I actually define what I want to know about physics. But this is kind of the first approximation. We want some sort of morphism that, well, every entry is a monomial. This seems to fit the description of what we want, monomial morphism. Now, let me start by saying, like arguing that this is not yet good enough, that we want more properties. So let's start with a non-example. So the non-example I'm going to give you this, we consider something from R to R2, very simple. That takes U, and then send into, what did I take, U2 or U3? To U3. U3, U2. So what is going on here is that you have R, you are sending it to R2. Oops. You're sending it to R2. And the image of the morphism now is going to be a change. Yes. Is going to be a cusp. Right? So in here it's going to appear that that phi of R is going to be contained, actually equal in this case, to x squared minus y third equals 0. So in the notion of the simplest possible morphism that we can take, this does not yet correspond because I can see that the image is yet singular at this point, right? And I would like to the notion. Sorry, yes, go ahead.
Yes, sorry, just to make sure things precise, you in your definition, phi of u is equal to xz or something like that.
Right. Sorry. So let me. Oh, right. There's no x here, right? This is x and y. Yes. Right. This is coordinates. Okay. So xz are coordinates at.
And also in the definition of monomial morphism.
Oh yeah, I haven't yet given the definition. What I did is like I'm saying like this is the first approximation, so maybe it should be a little bit more specific if there's doubt. So we fix some coordinate system at a point A and some coordinate systems at the image, so that when we do the so in here maybe I could add one more point here. When I write like this, I should really mean that I'm pulling back xi. And I'm making this slight abuse of notation. Does that clarify?
Yes, thank you.
Okay. Right. So coming back to, so this is not yet the definition. And one of the reasons for it is that if I just ask for this, then I'm asking that the target could be complicated. It could be singular, for example, in this case. So I don't want to admit things like this. This means that I want to define, I can see that it's going to be, the image is going to be containing something of dimension 1 here, and this is related to the rank. So I just want to define, want to make this remark and define what is called generic rank. So the little remark here is that if the rank of phi is constant equal to R, then the image is an immersed, not embedded, locally embedded, but globally immersed submanifold, Q submanifold. Of dimension R. So this is what is happening as this morph is outside of 0. So outside of 0, the morph is of rank 1, and therefore it is contained into some submanifold, analytic submanifold, algebraic submanifold of dimension 1. So it's going to be interesting for us. It's already an information here to define what we're going to call the generic rank. I'm going to call like this the phi. So phi A, the generic rank. This is going to be the rank of the Jacobian matrix of the phi at the point A. So as a germ at A. And this rank is not at the evaluation of the point. So I'm not evaluating phi at A. I'm looking at the germ at A. So this rank here is not in respect to the field given by R, but actually in respect to the fractional field of the quasi-analytic functions that we're considering the point. So in the example here, we're just taking the Jacobian. So just for the example, the Jacobian of phi of A, or phi of 0, sorry, this is just the derivative here, so it's 3u squared 2u, and we see that the rank of this matrix is equal to 1 in respect to the frac, right? In respect to the, we don't even have the frac, just in respect to quasi-analytic functions, it's not equivalent equal to 0, any one of the entries. So since there's something which is not equivalent equal to 0, the rank is 1. So one of the things that we're going to want is that based on this generic rank, we would like the image of phi to be possibly an analytic set, a smooth analytic set, not a singular analytic set, where the dimension is going to be given by this generic rank. Just as if the rank was constant, we'll get it. So one remark, we call it generic because outside of a set of measure 0, actually a quasi-analytic set, a proper quasi-analytic set, the rank is going to be constant, maximal, equal to this number that we're defining here. The actual rank is going to be constant equal to this. That's why it's called generic. Fair enough. Now let's move on to a second example before giving the definition, where I'm going to build up on this idea, and I'm going to think about another property that we would like. So example 2. Now let's look at an example that should be a monomorphism. I'm going to take U1, U2. I'm going to send it to U1, U1, U2 to the power 3, 0. So this is something that I would like to be. This does look like a monomorphism, everything is entering. And kind of based on what we're saying, should look at what is going on in the target, right? So here's z equals 0. So I do know that the image of this phi is going to be contained in z equals 0. But if I take here some little compact set, the image of it is going to give us a wedge like this. So it's not going to be true that the image is going to be something of dimension, it's going to be an analytic set. So this is to kind of highlight that what we're going to ask, the property that we want, is that the image of phi is contained in an analytic set, an analytic submanifold, quasi-analytic, sorry, Q submanifold. So smooth, in particular, let me stress this out, of dimension equal to this generic rank at a point I. So at least locally, this is going to be true. The generic rank of this, we can compute, is going to be equal to 2. It corresponds, and this is the heuristic that we can use, it corresponds to the maximal rank over an open-dense set of R2 here. So if we take points outside of U1 equals 0, U2 equals 0, actually just U2 equals 0 is enough, then the rank of the Jacobian is going to be equal to 2. So that's why the generic rank is also equal to 2. So this property is something that we do want here. We want it to be as simple as possible, and this is something that we can obtain. We cannot obtain in general that it's going to be exactly an analytic set, but that it's contained in a good one. Now, a second thing that this example is going to tell us that we would like to have is that if we consider another property that I want monomorphisms to satisfy is that it is open, because I'm not going to work in the algebraic case where I have affine open sets. So if we consider a translation, I want to A equals to say 0 psi with a psi different from 0. Then we consider a change of coordinates. Let u equals to u1, and I'm going to give a bad name, kind of on purpose. V tilde equals to u2 minus psi. So this new coordinate system is centered at A, right? At v equals 0, we have u2 equals psi. As u equals 0, we have u1 equals 0. That's the point A. And in these coordinate systems, when I take like this, what I obtain is the morphism given by u times v tilde plus psi to the power 3, 0. So in the definition of monomial morphism, if I want the property to be open, I probably need to admit situations of this form. But I can still make this a little bit better. This is not the best kind of form that I can do, because by the implicit function theorem, we may consider, let's say, maybe I should have, okay, this is a bit annoying, but I'm gonna write this. 9 plus v equals to v tilde plus e to the power 3, where this is just psi to the power 3. So by the implicit function theorem, I might still make a change of coordinates of this form, right? The derivative in respect to v tilde of this part here is different from 0, because psi is a thing different from 0. So I can make a change of coordinates so that it becomes like this, with the first entering in this eta. So once we do that, we obtain that phi uv is going to be of the form u v plus eta 0. This is kind of the situation that I'm going to admit as a monomial morphism later on. Okay. Yes, so maybe let me jump to the definition now, which is going to give us, which is going to have these two properties taken care of. Okay. I got confused. Where is the definition? Here. Okay, so now is the definition. We're going to say that, and I'm going to do it with the divisor already. Phi of md to ne is monomial at A, which is n in M, if there exists coordinate systems, just as usual. But now I'm going to actually introduce some new letters that are going to play some role later on. So the U will continue to be the variables which are exceptional. But in between the non-exceptional variables, I'm going to also consider differences between V and W. And this is much more of a technical thing, because later on in the proof, it's going to be interesting to separate the non-exceptional variable in two kinds, which I'm going to write. I'm going to come back to what they mean in a second at A. So here E is the product of the UI is equal to 0. D, sorry. The exceptional divisor at the source. And I'm also going to take X, Y, Z. Also in the target, it's going to be convenient to have some difference here. Y1, YQ. And here again is for a technical reason, which I'm going to explain in a second. And here I'm going to take P plus 1 S prime at phi of A. And the E is going to be the product of, oops, maybe it's too small here. Yeah. Is the product of the Xi's and the Yj's equals to 0. So all the X and Y are exceptional variables now. Okay. Z are non-exceptions. Such that, and now we have what we want, the normal form that we expect. Xj is equal to u to the power alpha j. J equals to 1 up until p. The y's, k, are going to be of the form u to the power beta k vk plus xck, k equals to 1 over k. So here I'm admitting this necessary change of coordinates, and that's why I'm calling them y instead of x. And then the z might be equals to VL for L equals to k plus 1 up until S, and otherwise it's going to be 0 for L equals to S plus 1 to this S prime that enter there. Okay, I have to add conditions here so that we have the two properties that we wanted. So being open is going to be kind of going to follow just because I'm admitting here this VK plus CK. But let me just go by a bit so that I can continue. Where the alpha J's and the beta K's are multi-indexes, as we are used to. The CK, they are non-zero real numbers. And now the two properties, two extra properties that are going to be useful for us. So the most important one here is that alpha 1, alpha p, how did I go to RQ, linearly independent. And I'm going to write a second before explaining the first. I also want the BK to be Q in the Q not in quasianalytic, Q in the set of rational numbers, linearly dependent with the alphas. Let me just first explain the first condition, and then I'm going to talk a little bit about the second. So the first condition, it guarantees that our first example, the non-example, was really a non-example. If we look at the first condition that we had, the first example that we had, U3, U2, then the multi-indexes that are appearing here is 3 and 2. They're not Q linearly independent, of course. So this is not going to be accepted as a monomial morphism. As a matter of fact, because of property one is enough in order to claim that what we want, one of the properties that we want. So let me write it down. Properties. One imply that the image of phi is locally contained in a smooth Q submanifold. So of course it is smooth, I'm just stressing this, of dimension given by the generic rank at A. So the rank, the dimension that it should, the minimal dimension, that the minimal in terms of the topology dimension that one can expect, right? Just like in this second example, it was containing Z equals 0. So this first property here just means that. So this is one of the properties. The second property is the monomial is an open property. And this is simply from the fact that we are admitting this VKs plus CKs that can happen. Now, just to explain a bit why the second property is to some extent not necessary, but very convenient so that we have the best possible normal forms, to get the best possible normal forms that one can obtain. If we don't use this, then we could have normal forms that could still be simplified. That's kind of the idea. So let me do this, present this with an example, a clear example why we are adding 2. So we take amorphous from R3 to R2. Let me take here U1, U2, V, and I'm going to send it to U1, not this one, it's done. Yeah. U2 square, U1 square, U2, V plus 1, because why not? There we go. So in this case, the terms that are appearing here, right? We're taking alpha equals to 1, 2, and this beta equals to 2, 1. So the beta is linear independent with alpha. It's not satisfying condition 2. And what you could do in this kind of situation is that you can still simplify the normal form that we obtain. So we can simplify by taking a change of coordinates. Consider.
Sorry, Andre, before you continue too much, I want to. What's the relation between the different numbers R, S, P, Q, and the generic rank of phi? Can we read it off from the expression directly?
Yes, it's going to be P.
It's going to be P. Okay.
Plus S.
P plus S. Yeah, it
Yes,
makes sense.
all of the V's
Okay.
contribute. If you think of the matrix, right? The Jacobian matrix, you're all going to have an entry, different entry for every time that you derive V, a unique entry which is non-zero. And for the use, you can use the fact that they are Q-linear independent. So you're going to have P coming from this part and then S coming from each one of the V's. So it's P plus S.
Okay, thanks.
So you consider U1 equals to, I got lost again. Yes. U1 V plus 1 minus 2 over 3, and U2 equals to U2 V plus 1 over 3. So these are changes of coordinates which locally are perfectly fine. So that now your morph is in terms of U1 tilde, U2 tilde, and this V is going to be just U1 tilde, U2 tilde square, U1 tilde square, oops, too fast, U2 tilde. So now the V doesn't appear anymore. So we use the fact that alpha and beta are not linear independent to say that we can make a change of coordinates that can be absorbed into the monomials. So that the coordinate V actually did not need to appear in some sense. The morph is going to be independent of this V. And this also explains now what is the reason why we have, sorry, I go too fast from one slide to the other, right? But what is the reason why we are singling out the W here? The W are things which are not appearing in the normal forms of the morphism. We call it phi free variables, because phi does not depend on them. So it's going to be it's going to come back, this W, the importance of this W in the last lecture when I talk about the proof itself. So for now it seems just technical, but when we talk about the proof, it's going to clarify about the monetization problem, about why it's interesting to single out this W variable. For now, it's just introduction of notation. Okay. No, there was nothing to prove here. So. Okay. Fair enough. We talked about the properties. So now let me talk about the main results. Let me start with the literature. Okay. So first of all, it's not in the literature, but in the case of dimension of the target of dimension 1 is essentially resolution of singularities, but we're going to see the proof in details later on. we need to use Sartre theorem. Well, or something else, but we need to use something about the critical values. But we're going to see it later on. We are also going to see in details the dimension m equal to 1 and q is the analytic functions or algebraic. Again, I do not know who's the first person to study that. Then if we look at the case dimension of m equals to the dimension of m equals to 2, then this was and q, these are the analytics. This is a result from, so positive result, I should say. Akbulu. And King from 92. If the dimension of m is smaller or equal than the dimension of n, which is smaller or equal than 3, and q is the algebraic, then this is a result of Kutkowski. In a series of papers from 2002 to 2015. And we also have local positive results. Which I'm also going to be precise, or algebraic. And this again is from Kutkowski. From then 1999 to 2017 in a series of papers. So this is kind of the state of the art, was the state of the art, and the problem was originally a problem considering algebraic geometry, so people focus on the algebraic case and sometimes in the analytic case. Now the results that I want to give to you, they're going to be true. At least today. So our first result is that no. What does that mean? It's the answer of the question. So there exists a proper real analytic morphism phi from m to n, and I think it's interesting to say that the dimension of m is equal to 3, and the dimension of n is equal to 4, which does not admit a monomization by global blowing up. As a matter of fact, the example is a bit stronger than that, in the sense that example is stronger. Phi, sigma, sorry, can be any proper surjective mapping with generic rank 3 map of generic rank equals to 3, and tau can be any proper bimeromorphic morphism. And particularly blowing up with weight, if you quotient after weight, right, if we do it in the way that it is still bimeromorphic, you cannot resolve it by using those. Okay, so this is the answer saying the original question, as we said, the answer is no. There is a counterexample of it already in the real analytic case. And then the positive result that we're going to give is then a local result. Again, over the truth. Now let me give you the positive answer. So let phi of MD to NE be a proper Q-morphism I prefer this one. Then there exists a countable a number of commutative diagrams and for once I'm going to just go scroll down so that I have the full view in one slide. So we're going to have a number of commutative diagrams. In B, we had our morphins phi going to NE, tau lambda here, and lambda, E lambda, and here the phi lambda commutative, such that so first thing, just as before in the local result that we presented, but with a little twist, sigma lambda and tau lambda are finite compositions of local blowings up and power substitutions. So I haven't yet defined what power substitutions are for us, and I'm going to do it later on when we arrive at the moment where this is necessary. So the plan is to give examples and to see why this actually is going to be necessary in the middle of in the general quasianalytic case. The second point is sigma lambda and tau lambda are semi-proper, as usual. And the third point is that phi lambda are monomial. So we get what we wanted, at least in a local way. Yeah. Did not think about this because I wanted to have the theorem and discuss about it. So I'm going to do it like this, although it's not the best organized manner to do this. But just a couple of remarks about it, this theorem. If the quasi-analytic class Q is equal to the analytic or algebraic, then the theorem holds with actually one prime, just as we did in the other. Well, no, we did it a little bit different, right? It was combinatorial blowing up before. Now our finite compositions of local blowing up. So in the case that it's analytical or algebraic, we don't need power substitutions. And this was the original result of Kutkowski too. This is the result that Kutkowski proves without the power substitutions in the algebraic and the analytic. So our result recovers this this property. And there is a moment in the proof that I'm going to try to pin out today already, because it's essentially considerations on the target where we're going to see it, this point. So what is the plan for today, for the last 55?
Excuse me.
Yes.
Andre, you ask also something about that the images of the M lambda cover M or something like that, or?
Yes, semi-proper covering, yes.
Oh, thank you.
Yes, yes. Thanks, Fernando. Yes, it should cover everything, yes. And it should be semi-proper. So semi-proper, I recall, for every compact set, there exists a compact set in the union of all of the M lambda whose image covers that compact set.
Yeah, as usual in local monomerization. Yeah.
Yes, yes, in the local result. It's what Felipe, I learned this from Felipe Cano, that if you don't use this property, then you should call it avoiding singularities instead of resolution.
Yeah. Okay.
How would you call it?
Thank you, Andre.
Okay, so what's the plan for the rest of today? I'm going to focus on considerations on the target. So this will mean that we're going to already talk about why in the analytic case we don't need power substitutions, but in the quasi-analytic case we do need power substitutions. And the plan is to have enough qualitative information to show what the example, to show explicitly the example. So this is the plan. So I will start now the third part of the talk. Once we have the result. And later on, what's the later plan, right? So Monday, I'm planning to talk about then applications of this result. And on Friday, about the proof of this result by making a dictionary with what we did with the local resolution. So for the next Friday, I'm going to really use what we did in the previous three courses to make some sort of dictionary between how we treat this case based on that one, which is kind of a simpler way that our approach works there. Okay, so let me pass to the next topic. This is a horrible line. Let me try again. So I call it the target. The first thing I want to consider is the case of dimension of M equals to 1. So the source, right? We have 5 from M to N. And I want to look at the case that the dimension of M is equal to 1. And let's start with a simple example here. An example is going to be phi from R to R2 is the example that we've already seen. What do we do with it, right? U that goes to, what was it again? I think I did U third or U square, maybe? U third. Right, I did this. Yeah. Okay, so we're going to do this example. And as we saw, we started here. And then we send to the R2. And then what we had in the image was a cusp. Whoop. E3 minus y squared equals to 0. So the idea is to transform this curve into a non-singular curve. So what we're going to do is that we're going to start by blowing up of the point here. Third time one. And we're going to see what we are going to define here. So we will define the blowing up of the point. So we're going to have an exceptional divisor. And then I claim that this curve is going to become, if you know resolution of the cusp, you probably know this by heart, but let me just point it out. So if you blow up here, let me just write the expressions. So I'm considering the chart x1, x2 equals to, I need to consider which chart, the x1 chart, yeah. x1, y1. So in here, it's going to appear that this red curve is going to now become x1 squared, x1 minus y1 squared equals to 0. So there is a component here which is exceptional divisor, which is the x1 equals to 0. But now there is a claim is that this morphism is well defined. Now I can verify this by hand by looking at the expression that I'm obtaining here. So what does that mean? I mean that I could take x1, and I know that x1 is equal to the entry x. That's why. Let me do like this. Sorry about this. So x1 is equal to x, which is equal to u squared. And y1 is equal to y divided by x, which is u3 divided by u2, which is equal to u. So now we have that the morphism x1 is equal to u squared, and y1 is going to be equal to u. So I do have that this guy is well defined. But there's a more general reason for this, which uses strongly the fact that we are with dimension of m equals to 1, which is the universal property of blowing up. So the universal property of blowing up says the following: if you take a center of blowing up and take another morphism, and the pullback of the ideal that generated the center is principal, then the morphism is factor through the blowing up. In here, if the dimension is 1, every pullback of every idea that you take here is going to be principal. So that's good. It's always going to function this. So we can, for the case of dimension 1 here, we can always just, in a simple way, just make this diagram work. And now we can continue the process, because it's still not monomial in the sense that, well, we wanted this, maybe I should have not chosen y, but z. Yeah, okay, but because this is not yet an exceptional divisor, we are not yet transverse the exceptional divisor, but if we blow up twice, we're going to get that eventually, or for the same reason, phi2 and phi3 are going to be well defined, and for the same reason, we're going to get that at the end, or our transformation is going to be now monomial. It's going to be now non-singular. So let's look at what happens with the morphism. We take theta 2. Oh, I think I made a mistake here. I wanted this to be y1. Hopefully this is not confusing. Equals to x2, y2, y2. Then we get that the new morphism here is going to be given by x2 equal to u, y2 equals to u. And if we do the last one, and then it doesn't really matter which chart we take. Come on, Andre. Then we're going to get that x3 is equal to u, and y3 is equal to 1. And we are one little translation of the target for this to be equal to 0, and to get, right, this little translation here, and to get a monomial morphism that we wanted. Okay. So the essential thing here was to blow up the target in such a way that the curve that we obtained was non-singular. So more generally, we take our phi of m to n. Let me simplify it. Let me do it in really one dimension so that I don't have to. Sorry, I wanted even to do it as a germ so that we really concentrate at a point. If we look at a morphism like at a germ from something of dimension 1 to dimension n, so in particular phi of 0 is equal to 0 according to this notation I just used, the germ notation, and we write phi as the entries phi 1, phi n, then of course either phi is constant equals to 0, or apart from a change of coordinates, apart actually from just reordering the indexes, we may suppose that phi 1 of u is equal to u to some power alpha times the function g of u, where g of 0 is different from 0, right? I have at least one function that is non-zero. I call it, it might be the phi1. Then I factor out, as it's one-dimensional, so I can factor out the power u as much as I can. And whatever is left is a unit. And the unit is quasianalytic because quasianalytic classes are closed by division by a coordinate. We can do better. We can change the coordinates. So apart a change of coordinates from a change of coordinates, we may suppose, so let me even do the change of coordinates will be u. I'm going faster than what I should. Is equal to u g of u 1 over a. Since it's a unit, we can do this. We may suppose that phi 1 of u is actually equal to u to the power alpha. Oh, no, wait, alpha, sorry for this. Can suppose this. And now I want to make, I want to specialize to the analytic case so that we make an argument. Okay, so far we did that everything was quasi-analytic, and we got it that we have this normal form where we start with phi1 of u equals to u alpha, and the other terms we don't have any, sorry, we don't have any information about them yet. They're just there. And I want to specialize the case that is analytic. So in the case that it's analytic, there's something that we can do. We can find relations for this curve in a direct way. So what we would like to consider in the target, so I recall our objective is to find this curve gamma, this red curve, right? If we find them, then we know how to start to blow up until we get some monomorphisms. That's, at least heuristically, that's the idea. So in here, we knew that it was this curve x3 minus y squared because of the form of the morphism. But we want to do this now in a systematic way. So if we want to do this in a systematic way, the thing that we would like to take to consider would be something of the form x2 or xi. Let me do xi already. Xi minus the phi of phi depends on u, but we know that this phi1 here of u alpha, right? So, which is going to be the x1 1 over alpha, right? Because if I call this entry here x1, then x1 should be equal to, sorry, then u should be equal to x1 1 over alpha in some sense. So this is what we wanted to consider, right? In the example, this would matter, would come to taking y minus x to the power 3 over 2. So this is not an analytic function. But we can do a little trick, which is usual in here, which is normal in this kind of setting, the algebraic and analytic setting, which is let psi will be an alpha primitive square of the unit, and consider Ri, which only depends on x1 and xi, given by the product from k equals 0 to alpha minus 1 of the xi, so the term that we are thinking here, minus phi of c to the power k on 1 over alpha. So what we're doing is averaging by a generator of the cyclic group here that of the alpha square root of the units. So in the example, which would be of order 2, which would mean that we are taking y minus x 3 over 2 times y minus, sorry, not really this. The power 3. So this is just going to be a plus, and what we're going to obtain is the cusp, right? So the claim is that when we do this, we get an analytic function. Well, and I'm not. I'm going to leave it as an exercise because it's not difficult to prove. Ri is analytic. Let's leave it as an exercise. So what have we done? We have found a relation in the target. What does that mean? It means that if I compose Ri with the phi, I'm going to get 0. Right? Yeah, I'm going too fast now. Note that Ri composed with phi is constant equals to 0. Right? At least at a the point at 0, the point that we are considering. Okay. So we do have the curve that we wanted, right? We can consider the curve. Gamma 0, which is R2 equals to R3, Rn equals to 0. This is going to give us a curve, a locally defined curve there. And then the little lemma that we can use here is that let tau from n tilde to this Rn be a resolution of singularities. Of gamma, then p tilde equal to tau composed with phi. Sorry, I have to be up. We have to p tilde such that p tilde again phi equal to tau composed with tilde is monomial. So now we argued that, so let me see. So in the case that we have analytic functions, we said, okay, we do know what kind of relations we want. We completed, we make an algebraic trick here to complete into a function which is actually analytic. Then we said, okay, this gives us an actual curve, an analytic curve, because we have n-1 equations. And in a similar way that we did for the first example, if we consider a resolution of singularities of this curve, I'm claiming that it's going to give us a monomization of that morphism. Okay. And the proof is also very simple. The proof is very direct. I don't think I'm not going to give the details. It's basically once you have the resolution, it means that you have a change of coordinates where the curve is going to become just z, like all of the other, just z2 equals 0, z3 equals 0, zn equals 0, which means that only the first entry, z1 is non-zero. And then you can verify in a simple way that it's a monomorphism. So I'm also going to leave this lemma as an exercise. It's also very simple. But then let's look at the case that it's Q is general. Okay, so all of this was done for the analytic case, and we used this trick. And in this trick here, we are actually using this function phi, which was analytic. I'm multiplying by something which is sometimes complex. And I'm using that in this case, the phi is still going to be convergent, right? Because if it's convergent at the origin, it's going to be convergent over at an open neighborhood, even in the complex case. So we are also using that there is a complexification. It makes sense to write this. In the quasi-analytic case, this is not necessarily, in the general quasi-analytic case, this is not necessarily true. And the difficulty, so Q general, no. So the difficulty arises from an example from Nazarov. Well, this example, by now there's several examples of this kind, but I like to use this one because it's very explicit. Although if I'm not gonna give the details, I'm just citing the reference. What they prove is that there exists a quasi-analytic class. And as a matter of fact, why I'm saying that there are other examples, because one can actually prove that every quasi-analytic class have property that I'm going to say here. And there exists a function f in Q of 0, 1. So it's a function defined. So let me just write it here somewhere. 0, 1, your function f into R, such that for every delta bigger than 0, and for every function g, which is quasi-analytic in between minus delta and 1, the restriction of g, to 0, 1, is different from f. So it's saying that whatever is the delta that we take here, whatever is the possible extension that we might want, there will not exist a function in the same class which extends this function here. So you cannot extend it to the other side. This contrasts with the analytic case, where if we know that the Taylor series converges at a point, we know it converges in the neighborhood. And it also contrasts with the same infinity case, where we always can extend a same infinity function by a same infinity function. It's not because of nothing that there exists a Weisser's preparation theorem for analytic, and there exists Malgrange preparation theorem, so the Weisser's version for the same infinity case in the same infinity category. It's very connected with the problem of extension, or actually of non-extension in the quasi-analytic case. So why this difficulty here creates a big problem for us in the quasi-analytic case? So let me go to an example, and I would like to have space. I'm going to go down. So I'm going to use this function f in the next case. It's simple. We just take from R to R2. We take U, and we're going to send it to U square, f of U square. Right, so we have here. And maybe the interesting thing is that since it's a U square, we're sending twice to the positive part here. What's going on? Right. So the situation that we're faced now is, change now, that if we wanted to have a relation, if we wanted to find the relation that is given by this morphism here, so a relation between the components and the target, it's not difficult to see what you would like to have, right? The relation that you would like to have access to would be R of x and y should be equal to y minus f of x, right? But this is only defined in 0, 1 times r. In particular, you cannot make, so we cannot make the change of coordinates, which we would like to do, z equals to y minus f of x. If we were able to do this change of coordinates, this monomial would become this morphism will become monomial, because what is this? This is just f of u squared minus f of u squared, which is 0. So we would get that we will get to the morphism would be given by u squared 0 monomial. But we cannot do this change of coordinates because it's not well defined in an open neighborhood of the origin. Right. So it's connected with the non-extension problem. And the phenomenon that we're looking here is not going to get better by blowing up. Blowing up is going to be a birational. Well, yeah, it's birational, but what do I mean by that, right? The fact that you cannot extend here, once you blow up, you're going to still have a whole half section that you cannot extend to. And this is not going to change by blowing up. Right, so this is the heuristic. You can prove it with computation if one wants, but just geometrically from the fact that you know that this part here is inaccessible by the extension. Whenever you blow up, you're going to still have something half plane, which is inaccessible in any case for the change of coordinates. So this cannot go better. So how are we going to deal with this? Now we can introduce power substitutions. Okay. So let me consider let R be some number in N and epsilon be plus or minus, be minus 1 or 1. So power substitutions in the real case, we're going to have things of the form u square. So you should have positive u square or minus u square so that you cover everything. So that's why there's going to be an epsilon here appearing. And then we can define, although if I'm not taking much care about the
sorry, Andre, before you go further, a very small question here. This problem that you just explained, is it related to this paper of Krzysztof-Nowak, which isn't the same theme of the necessity of the power substitutions, or not?
Okay, so what he proves in that paper, I just feel like this is a different kind of, it's more geometrical than that one, because what he proves is that you do need, so he proves that if f of x squared is, it's related with that, yes. Why didn't I think it was related? Yes, you're right, because he already gave the proof, an explicit proof using the Fourier analysis, right? That f of x squared is in a class, but f is not in the class itself, right?
Yeah, right.
Right, so it's connected. Yes,
okay, thank you.
Okay, so okay, so yeah. So the power substitution we're going to use here, although I'm not talking about, in general, we will want to do it only in respect to the exceptional divisor, although I'm not paying too much attention to the exceptional divisor at this talk, but just so that we define it in the way that later on, the strongest possible way. So what we will do, and the one here is just to say that the first one is the one that we're going to change, which should be exceptional and should be appeared. Oops, let me do this better. It's going to appear this epsilon, so either plus or minus 1, u1 to the power r. And then everything else is just the same. So we just replace one of them by the power r. And of course, if the power is even, then we should consider plus or minus, because otherwise we're not going to get surjective. We should consider both of them in order to get a covering. And in this situation here, let's connect. Okay, but no, I just want to talk about the class. I'm doing this kind of minimalistic. Okay, so once we do this, what we're going to do is we're going to do a power substitutions in the target in order to take away the ramification of u squared. So we're going to consider, consider whole of x tilde y tilde equals to x tilde square y tilde, which is this xy from the beginning, right? So we had that x is equal to u square, and it's equal to x tilde square. So from here we get x tilde equal to u, and y tilde is equal to y, which is equal to f of u squared. So again, y tilde equal to f of u squared. Right. And now we can make the change of coordinates. Z equals to y tilde minus f of x tilde square, because now this change of coordinates is defined over the open neighborhood in order to get monomial, because this is going to be f of u square minus f of u square equals 0, as we want. So now with a power substitution in the target, we were able to get monomial. Okay. So this exemplifies what's the difficulty in the quasianalytic case. In general, we cannot get relations in open sets like this. So that's why we use power substitutions. Right. So maybe just a couple of words coming back to the original part. Maybe I'm not going to write, but once you have this normal form here, once you have that phi1 is u to the power alpha, you can always make a power substitution so that it becomes just x1 equals to u, and then you just need a change of coordinates in order to get a monomorphism, because you just have to do essentially what we did here, right? For every one of the entries, because we already know that x tilde is equal to u, and all of the other entries are function in u. So it becomes very simple. So I'm not going to write this, but it's direct. If we use power substitutions for the case of curves, we can just get to this better normal form here by. Oops, there's some issue here. Yeah, you just can transform x1 to become by a power substitution equals to u, and then it's just a change of coordinates. So it becomes quite simple. So instead of that, I want to talk a little bit about the case where the source. So it's a little bit funny, right? And we're talking, I said that we're going to talk about the target, but we divided it in two parts. One where the source is equal, the dimension of the source is equal to 1, and the other one, the dimension of the source is bigger than 1. And I want to talk about difficulties. There is a first, and one of them I'm not going to spend much time, which is we did talk about the fact that we consider m to n phi, and we have a blowing up, and we should define this morphism phi tilde. So in the case of dimension 1, how to modify the morphism so that phi tilde is well defined. So this is a priori, like when we read like just what I wrote is not such a difficulty in the sense that we know what we have to do. We take the center of the blowing up, we take its pullback, we have to take a resolution of singularity of it. And then we're going to complete this diagram. We're going to have a true morphism coming from the source. It's going to factor out. The difficulty in here is that we're going to do this in a process of normalization. So we're going to have normal forms that we want to keep track of. So you cannot just do any kind of blowing up in the source and hope that you're going to preserve those normal forms. So there's actually a difficulty in this part. But in some sense, it's a difficulty that I'm not going to talk about it today, because I feel like it's a more technical difficulty that we know what we need to do. Like one needs to keep track of the normal forms. So we need to talk about the normal forms to say what are the conditions that we need to expect after blowing up to be preserved and etc. So it's going to be a more technical problem that we're going to cover in the other Friday. Today I want to focus on a second difficulty, which is more qualitative, which is obtaining relations. And here we can limit ourselves to Q equals to the analytic case is more than enough for us to have to discuss this case. Okay. In details. Okay, so the first thing is that in the case of curves, we were able to see that we were able to get, in the case the dimension of m was equal to 1, we were able to get n-1 relations. So we were able to get that the image of the curve was locally contained into an analytic set of dimension 1. So in general, we can define some sort of rank that measures this. And the definition of it, which I'm going to call like this, is the dimension of, so since I'm an analytic now, I can use usual standard. So this is, well, since I didn't introduce this, I'm going to use Q divided by the kernel. We take the germ and we take it as the pullback in terms of the local rings, and we take the kernel of it. But what does this? So this is the definition that gives me what is called the analytic rank. But the heuristic that because I'm not going to spend much time defining this, but it's the dimension of the smallest, and that's how we should think about analytic set germ containing the local image of phi at A. Okay. So in the case of when dimension of m was equal to 1, what we showed is the existence of R2, R3, Rn, so n-1 relations. So this means that this kernel here, this kernel is going to be given by this R2, R3, Rn. So when we take this quotient, we're going to get something of dimension 1. It's going to be the dimension of the algebraic geometry about the local ring of the curve. In any case, it's the dimension of this smallest set. Now, once we take dimension of m bigger than 1, then the fact is that this relation here, the number of relations that was connected with the generic rank might not be connected anymore. So let me just state this in a clear way. A definition, a point A in M is said to be regular for phi. So in the sense of Gabrielov, if the generic rank is equal to this analytic rank. For the case of curve, this was always true. Now, what I want to argue with you is that in general, this is not true. So this is a classical example of Osgood. We already talked about a bit. So if we take the morphisms that go from R2, maybe we can do to R3, yeah, and which takes from UV and it's sent to UV exponential V, I claim that the generic rank of this morphism at 0 is equal to 2, but this analytic rank is equal to 3. In other words, the only analytic set which contains the image of this morphism is going to be R3. There's not going to be something of dimension 2. So let's see why. Okay. Indeed, it's enough to look to show this formally. So let us take H, some formal power series in R3 here. So that takes x1, x2, x3, or x, y, z. Let's take an H in this sense here, such that when we compose with phi, we obtain something which is 0. So if it is a relation, if it's something, if we are in an analytic set and we compose with phi, which contains the image of phi, when we compose with phi, we should get everything equals to 0, right? Because that's what the function is going to give us. So we have this. So let's write H as the sum of homogeneous terms here. So in this case, when we compose with phi, what we're going to get, so at one hand, we know that it's going to have to be 0. We're choosing it like this. And we also know that this is going to be U alpha, H alpha of 1, V exponential V, which we want to be equal to 0. So now for each one of the levels that we consider, this is a polynomial in 1 V and V exponential V. But these guys are all algebraically transcendental between them. And H alpha is a polynomial. So there's only one choice. H alpha has to be 0 for all alpha in N, which implies that H needs to be 0. So the only formal power series, and therefore the only analytic function whose composition with phi is equal to 0, so that contains the image of, whose 0 locus contain the image of phi, is the function 0 itself. So this shows that the analytic rank is 3. So of course, if we start with this problem, we cannot use the last heuristic, right? We wanted to find enough relations so that this guides us, right? We are going to resolve the relations, and this should give us or approach us to have a monomial morphism. But now we have the issue that we don't even have a relation in the beginning. So one thing that we must do in this kind of case, if we want to get a monomization, just if we want to get some relations to start with the process, is that we should blow up the points which are the image of the points which are not regular, right? These points are going to be in the target. And we should blow up these points. These are the problematic points. They are really connected with the image. So we are going to blow up we blow up the points which are in the image of non-regular points. So in the case of Osgood map, there's only one point here. The 0, 0 is going to be sent to 0. So what we should blow up is the origin. In the example, we blow up phi of 0, 0, which is 0. in R3. Okay. We have our phi, R3, we have our tau. Oops, not M. I claim that we have this morphism phi tilde, and it's going to be enough to take the chart, the X chart. So now X is going to be equal to X1, Y is going to be equal to X1, Y1, Z is going to be equal to X1, Z1, and this computation we already done a couple of times today, so we know that X1 is going to be equal to U, Y1 is going to be equal to V, and Z1 is going to be equal to V exponential of V. And now we have a nice relation here given by Z1 minus Y1 exponential of Y1. So now the rank of Gabrilov, the analytic rank has decreased. We do have the relation that we want. Actually, we just need to make a change of coordinates in order to get a monomial. The change of coordinates given by W equals to this, so that it's only going to appear X1 equals to U, Y1 equals to V, and W equals to 0, and we're going to get monomial. So this example, we can deal with it quite simply by just blowing up the point. But this gives me, takes me to the last point of today, which is, okay, so now we've seen that sometimes we don't have relations, and we should blow up the points which are in the image of this, where we don't have relations, right? So what do I mean by this, right? We had these non-regular points, I'm a little bit confused, and we said we should blow up the image of the non-regular points. So the points in the target where there's no relation, or there's too few relations. Right. And let's explore that to construct an example that we cannot globally monomialize. So the example is going to be based on the Osgood mapping. So sorry, sometimes this happens. So the example of morphism, which does not admit global monomialization. And the example is going to be building in basically two kinds of functions. The first one is what we already saw, the Osgood mapping, which we just explained that it's not regular at 0, and we just verified that it doesn't have relations at 0. And the second one, we're going to take a function here, 1 over delta S minus 1 over pi. Let me just write delta, some number which is small, positive. Small. Start to write fast, I don't know why, I have time. Over pi. And the idea from this function is that what we actually want to consider is the sine of it or the cosine of it, both of them actually. Right? Which is going to give us something that at 1 over delta pi, we are going to accumulate, right? We're going to have something like this, as usual. And what we are actually going to consider is a curve given by h of s is going to be, where did I write it? Yes, there. Sine of theta s, which multiply cosine of theta s square, sine square of theta s. Yeah, close everything that I need to close. We're going to consider this function here. So this is the second one. The reason to consider, oops, no, I didn't close enough. The reason to consider this function here is because it will, its graph has an interesting property. The curve S gamma S contained in R3. So we are turning the circle here. We are also changing the, so in here cosine square, sine square means that as we go over, as we have an evolution with S, we're going to turn in the circle, and the function sign of theta S means that we're changing the radius along it. So once we get close to 1 over delta pi, we're going to actually be dense, and we're going to approach all of the points of the unit circle, right? Over S equals to 1 delta pi. So this curve here has an interesting thing that one can prove. The intersection of its intersection with any subanalytic set of dimension 2 is at most a finite number of points. Transcendental existence. That's nice. For all subanalytic set X, dimension of X is smaller or equal to 2. I didn't give a name for the curve, but SHS is only given by a finite number of points. So by this we mean that you locally finite. By this we mean that whatever we intersect, particularly if we intersect with something analytic, we're not going to be able to cover the entire curve. Okay. Very well. So now we can build up the morphism. So the base of the morphism is going to be the following application. We're going to take P, to use the same notation of the paper, from S3 to R4. So here, I'm going to write and then I'm going to explain. S U V W. We're going to send to S U plus H1 of S, UV plus H2 of S, UV exponential of V, where this S3 is equal to F square plus U square plus V square plus W square equals to 1. Right, it's this here. And we're defining this morphism here. So the interesting thing about this morphism is that the points where, that every point, if we follow the line S here, right? If we follow S00, whatever, what we need, 1 minus the square root of 1 minus S square, all of these points are not going to be regular. It's not regular. Zero, zero. Right. Around here. Moreover, P and P is proper. It's proper because it's analytic, and the domain is the sources. Oh, and the sources of the is compact. Let me just make the. Okay, so let me just write what is the issue here, right? So So what is going on is that we have this sphere, and we are looking at the target there. We're going to have the last coordinate here equals to 0, and then we have this curve of points S. Let me take another. In here we have this curve of non-regular points which are standing there. And what is going on is that this curve is going to be like a sinoid. And of course, we are only going so far, that's true. But if we wanted to extend this curve, then eventually we are going to get something transcendental, right? Because it would follow this H1 of S, H2 of S, and S would follow that curve that we considered before. So already this means that if this curve was global, right? If we want to resolve the singular, if we want to monomerize this morphism, we need to blow up the points which are not regular. So we need to blow up the red curve. In order to guarantee that everything is as it should be, let's just consider a new, just a small extra computation, and we consider this morphism R4, and we are going to take it in a manifold not M, and tilde, which is just the blowing up of R4. And now this is the morphism we're going to consider. So what did we do here? Tau, blowing up of the origin, and this I immersion to the, I could just write because we defined this already, sorry. The W chart. The chart in the last entry here. Okay. Where I'm looking at it as X, Y, Z, W. So if we do this, then this last morphism means that once we make the blowing up, so we will only have one point where there's no relation, we blow it up, and now we get that this is the exceptional divisor. So it's globally defined. And in this case, if you want to blow up the red curve, there's no way around it. You need to blow up the entire red curve. And if you say, okay, so maybe I can blow up something of dimension 2 or something else, then the property that any subanalytic set X will only have a finite number of points here means that for whatever sequence of blowings up, or more generally for every proper bimeromorphic mapping, the exceptional locus is going to be at least of codimension 2. It's going to be at most, sorry, of codimension 2. So its image is critical locus. So its critical values are going to be of a subanalytic set of at most codimension of dimension 2. And therefore, it will intersect only a finite number, locally finite number of points of this guy. So you're not going to be able to, by some other general centers of blowing up, cover this red curve by blowing up. So you're obliged to blow it up entirely, but this is not possible globally. So this is the idea of the proof. I'm sorry that in the end it was a bit fast, but I will finish here today. And the next time we're going to talk about applications. Sorry for passing a bit of time. Okay, I stop now.
Thank you, Andre.
Yeah,
Stop the recording.
Yeah, thanks. That's what I was.